So in this section in goodness of fit test, it's exactly what it is. I told you mathematicians are not creative. If we're looking for a good fit for something, we call it a goodness of fit test. And so we will use the goodness of fit test to um, determine whether discrete categorical random variable matches a predetermined expected distribution. So we could think about a coin, right? We expect when we toss a coin and we tell our peer, okay, call it, there's a 50-50 chance it lands on one or the other, right? Heads or tails. So we could toss that coin many times and we still assume with every toss there's a 50-50 chance it lands on heads or tails, right? We expect that probability of it landing on a tails or a heads to be 1/2, right? If it lands on a heads, that was a 1/2 probability because there's only two outcomes and one heads for the two outcomes. Well, how do we know for sure it's 1/2, right? Like, do we toss it enough? Like, how do we know that it's a good fit? How do we know 50% or 1/2 is the best fit probability for tossing a coin? Right? That's exactly what this test does. Does it say it's a good fit? If we had a six-sided die, the probability it would land on one of its sides is 1/6, right? One side out of six sides. How do we know that 1/6 is really a good fit for the six-sided die? Well, this is a test we can use to have to determine whether that is actually a good fit. So let's go ahead and take a look. So we can use the goodness of fit test as an inferential procedure to determine whether a frequency distribution follows a specific distribution. And what that really means is, does the frequency distribution, meaning 1/2 for tails or heads, or 1/6 for a six-sided die, follows that specific distribution, right? Well, we need to find the expected counts. Now, I can toss a coin 100 times and write those observations down, but what would I expect, right? And so we need to calculate the expected values on top of having observed values. And so they are expected counts are with n independent trials, an experiment with k greater than or equal to 3 mutually exclusive possible outcomes. P1 represents the probability, right? And E1 represents the expected count. So how we calculate the expected count. So if we have at least 3 categories, that means that we'll have P1, P2, and P3, and so on. And for each category, the expected count is represented by the mean of each account. And expected count is what we did before, right? It was just NP, right? The probability times the event. So N is given to us as a sample size. So let's just take a look at an example. So here, a sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to the U.S. Census, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than 1 year. 23.9% of grandparents have been responsible for their grandchildren for 1 or 2 years, and 17.6% of grandparents have been responsible for their grandchildren 3 or 4 years, and 35.7% of grandparents have been responsible for their grandchildren 5 or more years. If the sociologist randomly selects 1,000 caregiving grandparents, compute the expected number within each category, assuming the distribution has not changed from 2000. Okay, so how many categories do we have? We have the ones that the grandparents taking care of their kids 1 year, and then 2 year, 1 or 2, and then or 3 or 4, and less than 1 year, yeah, or 5 or more years. Okay, so we have 4 categories. So let's go ahead and let's see what that looks like. So K is equal to the number of categories. And so in this case, K is equal to 4. And so I would go ahead and maybe start a table, put like the years of caregiving or something. And that was like less than 1 year, right? 1 to 2 years, 3 to 4 years, and then more than 5 years. And so here, now what's the probability, right? So the percentage in each category. So we have observed in the year 2000, it is observed, right? So let me write that down. It's observed that grandparents that have been caregiving for less than 1 year is 22.8%. 1 to 2 years was 23.9%. 3 to 4 years, 17.6%. And then more than 5 years is 35.7%. So these are what's observed from the 2000 census. So now, what should we expect from this distribution, right? So now we're going to do expected counts, which is the number in our sample times each probability category. So this is the first category, second category, three category, fourth category. Okay. So what we do know is that we did take a sample of 1,000 caregiving grandparents. So of the 1,000, how many can we expect have been caregiving for less than 1 year? Well, that would be 22.8% of 1,000, right? So 0.228 times 1,000. How about caregiving 1 to 2 years? Well, that would be 0.239 times 1,000. And 3 to 4 years would be 17.6% of the 1,000. And 35.7% would be 0.357 of the 1,000. Okay, so that's how you calculate the expected count, right? You take the sample size and multiply by the category probability or percentage. And then you just go ahead and multiply that. So that would be 228, 239, 176, and 357. Okay, and then so these are the expected counts. So these are the values that are going to be the most important. So we need the categories 1 through 4, and we need observed percentages, the probability. Let me write that. The observed percentages from the census, and then multiply that by the sample size to get your expected counts. So right here are the expected counts. And so if we wanted to see the degrees of freedom, the degrees of freedom in this case is the number of categories minus 1. So we had 4 categories, and then minus 1, that's equal to 3. So you can see the degrees of freedom here, on a side note, is quite small because the number of categories you have is 3. So this is a chi-square distribution, and recall in the previous section we had stated that In order for the chi-square distribution to be more symmetric, the degrees of freedom would have to be larger than 90. So that means we would need at least 90 categories, right? Like 91 categories in order to meet that the skewed right distribution of the chi-square to move more symmetric. And so you could see that it's a lot of categories. So we have only 4 here, so this is definitely going to continue with the chi-square distribution.